In this video, we will look at homogeneous systems with infinite solutions. We will discuss how we can write those infinite solutions compactly as linear combinations of vectors. Suppose we have a homogeneous system and we want to solve it. Let's investigate this through a specific example. This will turn out to have infinitely many solutions. And the question is at hand is not how do we find them, that's just Gauss-Jordan elimination, but how do we write them down after we've found them? So the augmented matrix is this, and when we put this into reduced row echelon form, we get to this. I told you at the beginning that there would be infinitely many solutions, but the only way I knew that is that I wrote the problem. You couldn't just look at the original system and know how many solutions it had. Now, however, we see that there's a free variable. The pivot positions are here and here, which makes X basic and Z basic, but Y free. A homogeneous system with a free variable does indeed have infinitely many solutions. And to reiterate our goal, we obviously can't list them all. So how do we describe them? Let's start by writing down the equations corresponding to each row. As we write down the equations, notice that our basic variables don't mix. And what I mean by that is that each equation involves at most one basic variable. This equation only involves the basic variable x. This equation only has the basic variable z. The free variable appears in this equation. The free variables can appear in any equations, but each equation can only have one basic variable appearing in it. Also notice, each basic variable does appear in one equation. So we have as many equations as we have basic variables. If we ignore this useless equation, 0 equals 0. We're going to take the non-trivial equations, and we're going to rewrite them so that the basic variable is by itself on the left hand of the equality. So for that first equation, we're going to get everything except the basic variable x over to the right. This third equation already has that form. The basic variable is by itself over here. We'll come back to this space that I left in just a moment. Before we do that, let's try to get to this free variable y to appear in this equation as well as this equation. We'd like the free variable to appear in all of the equations. And we'll see why we want that momentarily. Well, that's easy enough to do. We have a 0 here. Certainly, if we multiply 0 by y, we still get 0. We haven't changed anything. Finally, let's write down an equation for our free variable. But what can we say about y? It's a free variable. It could be anything. Well, at the very least, we can say that y is equal to itself. Y can be anything, but at the end of the day, y has to be y. And we'll put a coefficient 1 in front of that y. And maybe now you can see why I'm doing all this. The numbers we're looking for, the variables, are x, y, and z. And what we found is that this vector of solutions can be written as the free variable y times this vector of coefficients. So here's our solution set. This is an infinite set of solutions because remember that y can be anything. It's free. So if you pick a specific value of y, say y equals 1, That gives you a solution. If you pick another value of y, say negative 1/2, that gives you another solution, and so on. Every value of y you pick gives a different solution. Another way of writing this is that the solution set is the span of this vector. In this video, we've started to investigate the solution sets of homogeneous systems with infinite solutions. We haven't yet stated an actual theorem. We just did an example and noted that in this particular example, the solution set was all the multiples of a certain vector. In the next video, we'll do a second example and state the theorem for solution set.